This video is for topic 8.5, acid-base titrations. The objective for this topic is to explain results from the titration of a mono or polyprotic acid or base solution in relation to the properties of the solution and its components. So the first thing we need to note when we're talking about titrations is what we mean by equivalence point. So the equivalence point is the point in a reaction when one reactant is totally consumed. So when we're looking at acid and base titrations, it's when either the acid or the base is totally consumed. When you're looking at a graph, the equivalence point is going to be where the tangent line is essentially vertical. So you're looking at the most vertical point on the curve. It's also going to be important to note the half equivalence point. So that is the volume halfway to the equivalence point. It's not the pH, it's looking at the volume. So it's the amount of solution to get halfway to the equivalence point. Both of these are different from the endpoint, which is the visual indication that you have reached equivalence or you have reached the end of your titration. The ideal is that your equivalence point and your endpoint are really, really close to each other because you want your indicator to be changing color right around your equivalence point. But the endpoint is based on the indicator, so that's the color change that tells you when to stop the titration. The equivalence point is the point at which we actually consume one of the reactants. So we're going to look at our different combinations. When we're talking about a reaction between a strong acid and a strong base, you have essentially your proton reacting with your hydroxide to form water. So the equivalence point is going to be when your moles of acid is equal to the moles of base. This is in a 1-to-1 ratio. So this would be a monoprotic acid with a standard strong base. The equivalence point for a strong acid and a strong base is going to be 7 because you're going to end up with water, which is neutral, and a salt is what you'll end up with at your equivalence point. Before that, you'll have more acid than base, and so it's going to have a low pH. And then as you add the base, your pH will go up until the equivalence point, which is at 7. And then as you pass the equivalence point, you will end up with excess hydroxide, which is where you get your higher pH or the second part of the curve. When we're reacting a weak acid and a strong base, so this is where we'd have a weak acid in our Erlenmeyer flask and a strong base in our burette, your pH is still going to be less than 7 to start with. So if we look at our pH curve or our titration curve, your weak acid is still going to have a low pH. It could be as low as your strong acid, but may not necessarily be so. And then when you react your weak acid with your strong base, you're going to end up with an equilibrium and you're going to create water. So the proton from your weak acid is going to join the hydroxide from your strong base, and you're going to end up with the conjugate base. At that point, your conjugate base can then act as a base and accept a proton from water to then form the equilibrium with its conjugate acid and the hydroxide ion. So this means at the equivalence point, so when you've reacted all of your weak acid, that means you have all conjugate base or A- in our generic reaction. Then we're going to look at the equilibrium of that A- reacting with water to form the weak acid and then the hydroxide ion again. So what we're going to end up with is an excess of hydroxide, which is going to make our pH at our equivalence point higher than 7 because we're going to end up with more base in our solution at the equivalence point because of that second equilibrium that's going to take place. And so because of that, that raises our pH. And it's that second equilibrium that determines what the pH will be. So it's the concentration of your conjugate base of your original weak acid. So that's the A- is what's going to determine, and then it's Kb. So that's what's going to determine the concentration of hydroxide in solution, which will then determine the concentration of, or will then determine your pH. This is where the halfway to the equivalence point comes in handy. When you have a weak acid reacting with a strong base, you're going to end up with a buffer region. So you might notice that the slope of the weak acid strong base curve looks a little bit different than the strong acid strong base curve. That region there, here, let's move my mouse. There we go. So now we can see the cursor. So this region here is the buffer region. Okay, so this is where we're coming up where it's resisting changes in pH. And so halfway to the equivalence point, if you derive Henderson-Hasselbalch, so if you use that equation, pH equals pKa plus the log of the ratio of the conjugate base to the weak acid. So when those two are equal, which is halfway to the equivalence point, you end up with 1. So plus log of 1, which is 0. So pH equals your pKa at halfway to the equivalence point. So if you know the Ka of your weak acid, you can calculate the pKa, because that would just be the negative log of the Ka, and then that will tell you what the pH is going to be at that halfway mark. So that can be a useful relationship. Okay, so now let's look at a different combination. So strong acid, strong base, still the same. Okay, so if you were to have the strong base in your Erlenmeyer flask and the acid in your burette, your titration curve would be flipped. So you'd start with a high pH and then it would go lower. Your equivalence point is still going to happen at 7. Okay, so that's not going to change because you're still reacting your proton with your hydroxide to form water, and then you'll end up with a salt. So whatever the anion from your acid and the cation from your base come together to be. And so your pH is still going to be 7 at the equivalence point. When we look at the reaction between a strong acid and a weak base, our pH is going to be determined by a couple of equilibrium reactions. So what we're going to start with is our strong acid. So here I have it written as hydronium ion, so H3O plus, reacting with our weak base to form the protonated conjugate acid, so BH plus and some water. So we're taking a proton from the H3O plus to add to the base, because that's what a base does. And then at the equivalence point, when you've reacted all of that base and you can't make any more, then your BH plus, so your conjugate acid, then gets to be an acid. Okay, so then it continues to react with water to form some of the conjugate, to form some conjugate base, and then some hydronium ion remaining. So your hydronium ion is going to be present in both the strong acid and in that equilibrium of the conjugate acid of your weak base acting as an acid. So in the secondary equilibrium that takes place. So because of that, because of the proton source in both of those locations, you're going to end up with a pH lower than 7, because the acid part of this reaction is going to win when it comes to its pH. pH equals pKa, halfway to the equivalence point, applies the exact same here. Okay, so halfway to the equivalence point, your pH will equal your pKa. You could also look at this as pOH equals the pKb if you're thinking about it in terms of base. If you don't want to do it that way, you can always use Kw equals Ka times Kb to be able to get between Ka and Kb. Because if you know one of them, you can figure out the other, because Kw is 1 times 10 to the negative 14. So you have to keep in mind when you're working with strong acids and weak bases, or weak acids and strong bases, you have to take into account that second equilibrium that's going to take place. So when it's a strong acid, the acid part is going to win, and you're going to end up with a lower pH. And so you have to take into account where your proton product is going to be, which comes from that second equilibrium. When it comes to your weak acid and strong base, the strong base is going to win. So you're going to end up with a pH higher than 7. And so you have to think about where that hydroxide ion is going to come into play, because that's what's going to determine your pH, which it comes into play in this second equilibrium here.